So hello again, and we are now in week 4. So September 21st. And this is our 7th lecture. And this lecture is on chapter 4, which is on scatter plots and correlation. Scatter plots and correlation. And we're going to start section 4.1 with the concepts of explanatory versus response variables. The difference between an explanatory variable and a response variable. So the definition is here in the book on page 99. It says a response variable. That's not how you spell it. Let's try this again. A response variable measures an outcome of a study. Measures an outcome of a study. An explanatory variable may explain or influence changes in a response variable. I say may, or the book says may, because it doesn't always. And in fact, one of the goals of a statistician is to ascertain whether or not one variable should have any influence on another. But at the end of the day, the explanatory variable is going to be your x-axis, and your response variable is going to be your y-axis. Okay, we have a, sorry, professor, I came in late. So, all right, let me update attendance. There you are, late, okay. So an explanatory variable is on your horizontal axis, and a response variable is on your vertical axis. And at a more advanced level of statistics, you might have more than one explanatory variables. You might have multiple response variables. But here, we're going to focus on one and one. One thing explains something else. And section 4.1 is very qualitative. There's no math in 4.1. It's just the idea of an explanatory variable versus response variable. But there are a couple examples here. One of them is this: how does drinking beer affect the level of alcohol in our blood? So do you think that the amount of beer that you drink should affect the amount of alcohol in your blood? Does that seem like a reasonable explanation for the response of that you're measuring? So if you didn't drink any beer, chances are that your blood alcohol level will be low. And if you drank a lot of beer, chances are that your blood alcohol level will be high, correct? So we would expect a relationship where as the explanatory variable increases, the response variable also increases, right? Now, can anyone think of an example whereas the explanatory variable increases, your response variable decreases? Think of an example out there in the world where as one thing goes up, something else goes down. Can anyone think of one? Doesn't have to be mathematical related. Beer and alcohol is not mathematical related. So can anyone think of something?
The more you brush your teeth, the less cavities you have.
Okay, the more you brush your teeth, the fewer cavities that you have. Or I think it's wonderful, right? The more you brush, the fewer cavities. The more you study, the less classes you have to repeat. I don't know. I'm sure there's many things we can think of, whereas one goes up, the other one goes down. Alexis, you're here. Okay, got you. Okay. Here's an interesting one. The more cars that you own, the longer you live. This is actually statistically valid, by the way, just so you know. There's a strong correlation, a strong connection between the number of cars that you own and how long you live. That people who have more cars tend to live longer than people who have fewer cars. Does that seem like that there should be a strong relationship between variables like that, number of cars that you own and length of life? It's statistical and the data supports it. Does that mean that if I want to live longer, I should go buy some more cars? Does that seem like a reasonable cause and effect relationship?
No.
No, but this is statistical fact that if you look at people who tend to own lots of cars, they tend to live longer. Can anyone think of a reason why something like this might be true?
Probably because the more cars you own means you have more money, which means you're rich, and money makes you happy.
Money does make you happy. I wouldn't know, but that's what I've heard. Money also buys better healthcare. All right. So yes, there is a connection. There's a connection, but it doesn't mean that one causes the other. People who tend to have more cars, or people who have more cars tend to have more money. People who have more money tend to have access to better doctors and better healthcare and overall a better quality of life with less stress, etc. So there is a statistical connection between them, but just be aware that correlation, which is how much they're connected, does not necessarily mean causation, that one causes the other. There could be variables lurking behind the scenes that connect the explanatory variable to the response variable. Here's another one. A very famous example that the more ice cream you eat, the more likely it is that you're going to be attacked by a shark. The more ice cream that you eat, the more likely it is that you'll be attacked by a shark. This is, again, statistically valid. Can anyone think of a reason why someone who eats more ice cream might be more likely to be attacked by a shark? Do sharks say, hey, I like ice cream. I can't get it because I can't go on land and go to the ice cream shop, so I'll just eat someone who had ice cream. Does that seem like the reason why this might be the case? No, the reason is people who tend to eat more ice cream tend to be where, or might be where?
At the beach.
At the beach, or certainly in the summertime, and et cetera, where if they're at the beach, they might be more likely to be attacked by a shark. So again, we have a situation where there can be a connection between two variables, but it does not automatically mean that one implies the other. Okay, and we'll talk about that more in this section, because this whole chapter is about correlation between variables and how much two variables are connected. But be very aware, and I'm going to repeat this over and over and over again, very famous phrase, correlation does not imply causation. Just because two things are connected does not mean one causes the other. There could be a lurking variable, something behind the scenes that's connecting them. So 4.1 is the idea of explanatory versus response variables. 4.2 is on displaying relationships, in particular scatter plots. Now, in the last few chapters, we talked a number of times about displaying various relationships. We had bar graphs, we had pie charts or pie graphs, whatever. We had histograms, we had box plots, we had what else did we have? We had stem plots. We had all these different things, and we never talked about scatter plots. Didn't mention it once, not a single time. Why did we not mention it once? Well, for the very simple reason that a scatter plot wasn't applicable to any example that we spoke about so far, Because every example that we did so far was all about a single variable, one variable at a time. We never spoke about multiple variables at the same time. It never came up in conversation. Here, we have two variables at once. And we're looking at the relationship that connects two variables. So this is a new scenario that we haven't had so far. Two variables at the same time, and we're interested in whether or not one has any effect on the other, either via causation or just straight up correlation. So a scatter plot, is a plot. That's good. I mean, that's the word plot in there, so that makes sense. Is a plot that displays the relationship, that displays the relationship between two, and this is important, quantitative variables. They must be quantitative. We do not use scatter plots for categorical variables ever. Scatter plots are for quantitative variables measured on the same variables. Same individuals. So for example, how many cars you own, how long you live, how much time you spend every day brushing your teeth, how many cavities you have, and so on. Each individual in the data set or in the data appears as a point. In the plot. Fixed by the values of both variables for that individual. So this is the lengthy definition of a scatter plot. But at the end of the day, what is a scatter plot? You have a number of individuals. For each one, you're measuring two variables, what's going to appear on your x-axis and on your y-axis. So each point, each dot in the diagram is one individual. So let's say, for example, you are measuring the following. Let's say you're measuring, just a bit very straightforward, a simple example. Suppose you are measuring age in months versus height in inches. Suppose you are measuring age in months versus height in inches. So I go to the hospital. And I go to the delivery area and I check out some babies. They're of course 0 months or fractions of a month, whatever. They're very young. Or maybe I go to a pediatrician's office and I measure, toddlers and infants and young things, young people. What do I expect to happen as the age increases? What should happen with the height for each individual that I look at? What's a pattern that I expect? I would expect the height to increase. But do I expect that to increase indefinitely? Or is the rate of increase for young people different than the rate of increase for older people? Okay,
Yes.
different. Now, does everyone increase at the same rates? Do people the same age automatically have the same height? No. So I would expect possibly a relationship that might be looking like each of these is an individual, and maybe something like this might be a appropriate scatter plot with, you know, a few outliers now and again for abnormally tall or short people. But something like this might be a scatter plot for age versus height. Each dot represents one individual, and you have some scale on your horizontal axis and you have some scale on your vertical axis. And what we're trying to see is whether or not there's a connection between one variable and the other. And luckily, we have formulas for this. The calculator is going to do it for us. We don't got to do it by hand. We can do it by hand, but that would be really horrible to do. So we're looking for graphical relationships. We're looking for mathematical relationships. In this case, I certainly see in my make-believe scatter plots that there is a increase over time, and it tends that over time it kind of tapers off, and it does not grow as fast as it does in the beginning, right? There's certain like a curve that goes through it, which would seem to indicate a tapering off quality. Does that make sense? Yes. So a scatter plot is really a lot easier to see versus this long-winded definition explaining what it is. You see a picture of it and it's kind of like, oh, that's a scatter plot. Does that make sense? Okay. Does that make sense, everyone? Okay.
Yes.
So now 4.3 is on interpreting scatter plots. Interpreting scatter plots. So what are the things that we look for in a scatter plot? We certainly look for the overall pattern. We look for deviations from the pattern, Right, if I had a dot down here or way out there or something like this, right? Those are like, hey, what are those guys doing there? That doesn't make any sense, right? Those are deviations from the pattern. In terms of the overall pattern, we look for direction, we look for form, and we look for strength. Those are the three big ones: direction, form, or strength. Now, usually when we talk about direction, we mean, is it going up or is it going down? Positive or negative? Is there a positive relationship or is there a negative relationship? In this example, would you say there's a positive relationship or a negative relationship?
Positive.
Positive, right? Our example, direction positive versus negative. Our example is positive in the sense that as one goes up, the other one goes up. Of course, you could have one where it varies, goes up, then goes down, but those are more complicated. We're trying to keep them, you know, relatively straightforward at our level. And we have positive versus negative. Okay, all good so far? Okay.
I have a question.
Yeah, go ahead.
For the second bullet point, is that outliers?
Outliers.
Outliers, okay.
Outliers. You're knocking my handwriting, I see. Okay, I see how it is. Okay, that's how it's going to be. All right, outliers. Form. In this class, the form is basically two possibilities. Either it's linear or nonlinear. We're not going to really worry, I think, at all about if it's not linear, what form it has. Is it quadratic? Is it cubic? Is it exponential? Is it logarithmic? We're not going to worry about that. It's either linear or nonlinear for our class. Okay, is it a line or is it not a line? And then strength is how strongly does it follow the pattern that we are suggesting. Like for our example, would you say that our example is linear? No, no. I mean, if it's linear, it would keep going up forever indefinitely, which we know does not happen. I'm not 86 feet tall based upon my growth rate as a child. Okay, so it's nonlinear. It looks like it's, a curve like this, which we're not going to give a name to. I'm not going to worry about, is it a logarithmic curve? Is it a square root curve? Is it this kind of curve? It's just nonlinear. But the question is, how strong is that relationship? How tightly is it to the curve? Is it really, really tight around the curve? Thank you. Is it really, really tight around the curve? Or is it somewhat around the curve? Is it so bad that you can't even see that there's really a relationship in the first place? This is what we mean by strength. And as we're going to see later in the chapter, we can actually quantify that. We're going to have a formula that's going to give us a number. And from the number, we're going to be able to say it's very strong, it's moderate, it's weak, it's very weak. So, you have strong, essentially you have strong, moderate, weak. And we are going to be able to quantify that, give a specific number, and from our number, be able to answer what it is, because it's really hard sometimes to look at a scatter plot with your eyes and say, oh, that's strong or not. Sometimes they look strong and you calculate it and you're like, oh, that's not strong at all. Or sometimes they look like they're not strong and you calculate it and you get a very high strength coefficient. So we'll get to that later. So these are the overall things that we're looking for scatter plots. Okay, so are there any questions so far just on the very non-mathematical idea of a scatter plot, what it does, and what you're looking for when looking at a scatter plot? Is it so far so good?
I have a question about the scatter plot with the height and the age.
Sure, go ahead.
Would we describe the form as linear, or can we say it's curved?
I would not say this is linear. Because if it was linear, it would keep rising indefinitely at the same rate. And we know that, or hopefully we know, that adults do not increase their height as quickly as children do.
So what form would we describe that?
Nonlinear.
Okay.
Nonlinear, the best we can say is nonlinear. We're not going to get into the details of all the other types that it might be and worry about which one it is. If you ever become a statistician or someone who has to write a thesis that involves statistics, then of course it's a whole different story. But at our level, it's linear or not linear is all that matters. Okay? Now, section 4.4, still very non-mathematical, very qualitative. Adding categorical variables to a scatter plot. So first, very important, to have a scatter plot in the first place, you need two quantitative variables. Okay, you cannot have a scatter plot unless they are quantitative. What we're doing now is not replacing them with a categorical variable. What we're doing now is adding some feature to our scatter plot. For example, in the example I have above of age versus height, what is a categorical variable that I might be inclined to keep track of when looking at my scatter plot that I think, you know what? Oh, I just made up these examples. This one's at the top of my head. This is not a in the book. But again, for this example here, you go to a hospital or to a pediatrician's office and you get all this data on children, age versus height. And you say, you know what? I see two striking patterns here. Maybe I should separate those two into two different scatter plots, but yet have them overlaid with each other so I can see them at the same time. What would be an example, a practical example in my age versus height example of, so gender, wonderful. Maybe I want to differentiate the boys from the girls, again, not getting into gender fluidity, just biological. So I want to separate the boys from the girls. How might I do that? How might I add that categorical nature to the scatter plot that I already have? How might I include this aspect of categorical? Well, what do you mean by a title? Okay. One example is color. Use a different color for the boys and the girls. Boys in blue, girls in pink, very traditional, very archaic. Maybe we'll change it up. We'll do boys in green and girls in chartreuse, which is a color, but to be honest, have no idea what it actually is. I think it's blue, green. Anyone know? What's chartreuse? Shade of green. Okay, so I need a different color then for boys. I'm going to use magenta, which is again something that I don't know what color it is. I think it's like a brownish color, maybe a purple. 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 Okay. So whatever. The point is, if you want to add a categorical data, one way is via your colors. Can anyone think of a different way of adding a categorical shape? Like, what do you mean by that? What do you mean by shape? Yeah, squares versus circles versus triangles versus stars, right? That's an example, of course, where you can have more than one. Well, colors also, you can have, as many colors as you want. Of course, the more different categories you have, the more complicated it becomes. But in theory, you can do it. Does that make sense? So for 4, very straightforward, to add a categorical variable to a scatter plot, use different colors or shapes. I don't even know if, the book just says use colors or shapes. Can anyone think of anything else besides colors or shapes that you might use? Personally, sizes, well, the thing about sizes is, especially if you have lots of data points, is you don't want to have them get in each other's way so that they kind of overlap. And if you use different sizes and points are close to each other, that might be a little confusing. Now, I would suggest not using sizes, especially because each individual, boy, girl, whatever, is at a very specific X and a very specific Y, and it truly is a point. So I would suggest not sizes. Designs or signs. What do you mean by that? Design is the shape, right? Yeah, so I think those are the 2 big ones. All right, so any questions so far? Very non-quantitative so far, this chapter. All right, I would go so far as to say categorical, but that doesn't really make sense. But it's not very numerical. Until now, section 4.5. Measuring linear association. Measuring linear association, and we call that correlation. So first, it's very important to understand that what we do now, this mathematical technique that we're going to do, measures linear association. If you have a scatter plot that looks like this, oh, thank you. Would you say that scatter plot, that there is some kind of association between the X variable and the Y variable? Some kind of association. No, not at all. I see it's not linear, but I definitely see a pattern there, right? very quadratic looking, very parabolic. I don't know offhand some kind of situation that would create a shape like this, but there certainly looks to be a pattern. What we do now in this section will not tell us that there's a strong relationship, because what we're learning is only about linear associations. It will tell us how strongly the data represents a linear relationship. If it's not linear, the technique will not work. And you have two options, both of which are beyond this course. One is to design a mathematical relationship for nonlinear situations, which we're not going to worry about. And the other way is to recast the data in linear form, which again, we're not going to worry about. The fact is, for this class, all we care about is linear associations and measuring them. So if you try to measure a nonlinear association with this technique, the result will probably come back that it's not linear. And you'll say, oh, look at that numerical value that I had. There's no association. No, that's not correct. There's no linear association, but maybe there will be an association anyways. So this is nonlinear. So don't try to use correlation. The correlation, which is what this section's about, is only for linear relationships. Have I repeated that often enough in the last 2 minutes that you won't forget it? I hope so. I hope so. So, how do we find the correlation? Here's what we do. Again, I'm going to give you the formula, which we're never going to use. We're never going to use this formula because our calculator can do it much faster than we can do it by hand. But it's good to know the formula anyways. So your data will be a collection of points. The first x1, y1, the second x and y, so x2, y2, the third x and y, so x3, y3, all the way to the nth x and y. You have n data points. Each data point has an x and a y value. So you have your data. Here is how you measure the correlation, which is given by the symbol R. It's 1 over n minus 1. And then what we're going to do is take the first x value, x1, minus the average of the x's, minus the mean of the x's, and divided by the standard deviation of the x's, and multiply that by the same thing with y. So y1 minus y bar over s of y. And we're going to add that and do this for each one. This is the formula to calculate the correlation. Personally, I would not want to do this by hand. So what we're going to do is we're going to do an example from the book and do it on our calculator. So here's an example. We have the following. That's not what I want. We have the following data set. It's only 5 data points. And we're going to measure the following individuals. So we have temperature versus growth. And this is for some coral reef somewhere. So apparently someone said, you know what, I think that the temperature of the water should affect the growth rate of the coral reef. and it measured 6 temperatures. It measured 6 temperatures. And it also measured the growth in whatever units that we're dealing with here. I would assume that's Celsius. And the growth is actually in centimeters per year. So this is centimeters per year. And this is in Celsius, degrees Celsius. And the question is there a linear association between temperature and growth rate? Okay, so calculator time. Does everyone have a calculator by now?
Professor, on the second row at the end under Celsius, what does that say?
Centimeters per year.
Thank you.
No problem. Okay, so last time we used the calculator. We went to distribution, correct? Second DISTR. You guys all remember that? Hopefully from last time. Yes, no, maybe so. Other one? Acknowledge my presence, please. Okay, this time, something very different. I want you to hit the stat button. Stat button is right in the middle on top, or third line. Stat, S-T-A-T. Can't miss it because it says stat. You all see it? When you hit the stat button, you're gonna have something that looks like this. You want to hit enter right away because we're going to edit. And what we're going to do is we are going to put in list 1 and list 2, we are going to put in our data points. So for the first list, we have 26.7, 26.6, another 26.6, 26.5, 26.3, and 26.1. And for the second list, we got to match them up. So 0.85, 0.85, 0.79, 0.86, 0.89, and 0.92. So when you do that, you should have it look like this. Are we all with me so far? Anyone not with me? So I want you to hit second quit. After you put it all in, you can quit out of this. You go back to this to the regular mode, second quit. The quit button is right next to the second on top. Second, and then quit right next to it. Second quit. And then I want you to hit stat again. But this time, we're not going to edit anymore. We're going to go to calculate. Okay, and I want you to go to second, two variable stats. Actually, I lied. R is not on there. So go back to stat, calculate. This time go to the fourth line. Linreg AX plus B. And hit enter, and then go through it to calculate, hit enter again. Now, when you're all done, you should see this if your calculator is programmed to do so. If not, I got to walk you through a diagnostic setting. And so if you go to the bottom and hit calculate, this is what you should see. If
Mine just says A and B. I don't have the R.
Okay. So what we need to do for you and anyone else who's here is I want you to hit second again. And this time at the very bottom, hit catalog. Right above the 0, you should hit catalog. Okay, so when you do that, you should see the list of lots and lots of things in this calculator. And I want you to scroll down all the way to diagnostic on. So if you hit the look down button, it will scroll automatically. I want you to go all the way down to diagnostic on. I want you to enter. I want you to enter again until it says done. Now let's try it again. Stat, calc, linreg, ax plus b, calculate. And now you should see the R. What's the R that we get?
Which R do we read?
Sorry?
Which R do we read though? Because there's R squared and then R.
Just R.
0.81.
Negative 0.81,
Oh yeah.
right? Very different. Negative 0.811 approximately. Is everyone with me? Did everyone get that?
Yes.
What do you think the negative tells you?
If it's a positive relationship or if it's a negative.
So Nikki, the negative is not the strength. The negative is either positive or negative relationship. In this case, it's telling me that I have a negative relationship. Okay? A negative relationship. The direction, yeah. So does it go up or does it go down? Now, even though it's the next chapter, I'm going to throw this in now because we have it in the calculator. The first line reads y equals ax plus b, correct? The second and third line tell me what my a and b are. So in our example, I get y equals negative 0.157894736 plus 5.3038947368. Agreed? So now I want you to do something else. I want you to hit the second again. And right above second, hit stat plot. Do you see stat plot, the very top left corner? So stat plot. And the very first one, plot one, I want you to turn it to on.
Can you repeat that?
Yeah, hit second stat plot. Okay, second stat plot. And I want you to turn this one to the first one, plot one, hit enter, and turn it from off to on. You should see a screen that looks like this. And you want the on highlighted. Okay. Now, go to window. Go to window. Top line, go to window. What X values do we want our graph to include? From what to what? Look at your data. Look at the data and tell me what X values we want to make sure that our window is going to include. From what to what? Min to max. So in our example, what is min to max?
0.79.
No, the X value, the temperature is X because it's affecting the Y, correct?
Yeah.
So what's the X? From what to what?
26.1 to 26.7.
Okay, so I'm going to do, just to include it all, 25 to 28. That will make sure that I include my data and not go too far away. And what Y value should be my min and my max?
Uh, 0.79 to 0.92.
So if I want to make sure I have them with a little room to spare, what should my Y min and my max be on my window? From where to where? What's a good choice?
0.75 to 0.95.
I did 0 to 2, but it's your choice. As long as you cover it, as long as you cover it, it's fine. I did 0 to 2. But do whatever you like, as long as you cover the range of values. And when you hit graph, this is mine. Okay, with my window, when I hit graph, this is what I have. Now, did you all get that or something similar depending on the window that you chose? Does this look, oh, very nice. Does that look fairly linear to you? And just be aware, linear does not mean exactly on a line. Linear means, do you see that the overall pattern is roughly aligned? Now, so the answer is yes, I see a line here. I see a line. The question is, how strong is that line? Well, my R value was negative 0.811. What I'm going to do with that R value is I'm going to square it. Now, if you go back to stat, calculate linreg AX plus B, you'll remember that they gave me the R squared value. They already squared it for me and got what? What was my R squared value?
You
Go back. Huh? Yeah, 0.6578, right? 0.6578 or 0.658, whatever. This is moderate. This is not a very strong relationship. As we're going to see, we're going to be given numbers later in the course. In next chapter, I think. And we're going to see that 0.658 for your R squared value is not really that strong. Okay, it's moderate. So we have a moderate linear relationship here, which is negatively correlated. And in fact, when you see the graph, do you agree that it's going down as you go right to left to right? Now, to show you one more thing, hit Y equals, not stat plot, but just Y equals. Should have this screen right here. Y equals is the top left button, Y equals. Put in your function, AX, so negative 0.15789, you don't got to use every decimal, I use 5, plus 5.03895. So I put in this right here. My Y equals AX plus B that I got from my calculator. And this button here, hit this button, you get the X. XT theta N, hit it once, you get an X. So negative 0.1578, whatever, I can't read backwards, X plus 5, whatever. And then hit graph again. Do you all get this? Okay.
I didn't, my line didn't go.
Sorry?
I didn't get a line when I did it.
What do you have as your Y equals? What do you have as your Y equals? Read it to me, please.
I have negative 0.15789
Yeah.
plus 5.
Wait. X.
Oh, it's-
X.
oh, after the Y?
Yeah, right here. X.
Oh, okay, thank you.
All right, it's MX plus B. It's got to be it's got to have the X. That's all you need a calculator for. That's it. No more calculator for this chapter. Calculate R squared, A and B, graphing them, you now know how to do it all. You should get this. And if you change your X values to, let's say, 26 to 27, and your Y values from, let's say, 0.7 to 1.1, that just spaces them out a little bit because you're making the window smaller. So it just spaces them out. Now in the last one, I'm like, oh yeah, that's very linear. But now it's like, oh, well, how linear really is it? Those dots, some of them are on the line, but there's a few of them at the end that aren't. This is the danger of doing it by eye, because depending on how much you zoom in, it might look linear when it really isn't. Does that make sense? Any questions on anything that we've done so far? Yes, yes, we have a question, or yes, or I'm not sure when that was at. No, that must be 2 minutes ago. Is there a way to borrow or rent this calculator, or where I could find it? The school does rent them out, I think from the bookstore. I don't think they're that expensive. And you can certainly rent one for a couple months, I think. I'm pretty sure. But just while we're here talking about all these topics, let's do it on StackCrunch as well. And let's see how StackCrunch handles it. So I'm going to go to Math 140 Science. And anyone know if there's any StackCrunch assignments in this one, or yeah, I can go to chapter 1. Well, you know what? This is chapter 4 now, right? So chapter 4 homework. I'll load it up. I'm sure there's going to be some StackCrunch ones. Let's go to, let's see this one. So no StackCrunch here. Bad choice, bad choice. Okay, I'll go back to chapter 1. I know it's there somewhere. Well, actually, no, I want to do this. Let's try this one. Oh, no. Is there any StackCrunch anywhere? How do I find StackCrunch, guys? You guys know better than me. How do I find StackCrunch? There's got to be a way to find it, right? Anyone know? I know what I can do. I know what I can do. Okay, I got it. I got it. Ebook and scatter plots. I know what I can do. Okay. I figured it out. Okay, and then we're going to go to measuring linear association correlation. Okay. And okay. How do I scroll down? Oh, here we go. Okay. Okay, so that one we just did. Okay, let's go to the exercises. Okay. Okay. Here we go. Here we go. Okay.
I'm pretty sure you can press that crunch it symbol.
Yeah, I'm just looking for a good example to do. One that looks interesting. So, okay, poverty and life expectancy. Why not? So, do poor people? Because this is related to the car thing we spoke about earlier. Do poor people tend to have shorter lives than richer people? Two researchers ranked all counties in the United States by their poverty level, divided them into 20 groups, each representing approximately 5% of the overall US population. The bottom 5% were the least impoverished, the wealthiest, and the top 5% were the most impoverished. Life expectancies at birth for each of the 20 groups were calculated based on life tables. Here are the data for poverty percentiles. Higher percentiles is greater poverty, and life expectancies at birth. Okay, so let's make a scatter plot. Let's hit crunch it. And here is all the data, which is nice. When you link it from the assignment, it automatically puts in all the data. So the first question is, which of the tabs do you think we're going to use? Lately, we're using this one, but that's when we had normal distributions. We don't have distributions here. We're not hitting the DISTR tab. So is it a graph? What do you think? Is it this one? Well, which tab of these do you think is the correct one? And if you're not saying scatter plot, you're not listening, because it's really can't be anything else. So let's go to scatter plot. X will be my poverty percentile rank. Y will be my male life expectancy birth rate. Group by, no, we're not grouping by anything. It's only optional. I don't want to do it. We're going to show points. And let's calculate it. Okay, so this is my scatter plot. What kind of association do we have here? What kind of association is this? Anyone? Positive, negative? What is it?
Negative.
Negative, right? It's certainly going down. From your eye, would you say this is strong, moderate, or weak? Remember, strong is very linear. Weak is, can almost barely tell that it's linear. And moderate is, yeah, it's linear, but it's not, you know, it's a little off perfection. So I get mod. I got stuck in the window part. I want to enter moderates. Oh, I think you were answering two questions at the same time. Flower. I think. Let's do it. No problem. Okay, so now we want to get numbers here. So I think it's going to be statistics. Let's find it. Because with scatter plot, I didn't have a way of getting a value. So let's find it. Let's see, maybe it's descriptive. Columns. No, I don't think it's this. Oh, correlation right there. Correlation. Here are my two variables. Let's calculate. So I have a correlation coefficient of negative 0.9239. Do we agree that it's negative? Does the graph indicate that it's negative? Yes. Okay. Our R value is negative 0.9239. If I square that to get my R squared value, I get 0.85. 0.85 is fairly strong. As we're going to see next chapter, I think next chapter, I don't think we do it this chapter. The highest R squared can ever be is 1. If you get an R squared value of 1, then all of your data falls exactly perfectly on a line. So close to 1 is strong. Close to 0 is weak. Our R squared value is 0.85. 0.85 value is fairly strong. So it's actually interesting. The last data on my calculator looked strong, but gave me an R squared value of 0.65, which is moderate. This one looks moderate, but gave me an R squared value of 0.85, which is strong. So again, we use eyesight to have a general idea, but we use the calculator or crunch it to get the actual value, because nothing beats the actual value. So we did it on crunch it, we did it on our calculator. We did not do it by hands. We're not going to do it by hands. Nobody wants to do it by hand. That's just stupid. Don't do it by hands. Okay. So any questions so far on what we're doing and why we're doing it? Yes, makes sense? All right. So now, section 4.6, the last section for today, facts about correlation. Facts about correlation. And in fact, actually, I want to do one thing here with you that's on my screen on the ebook. So I want to share this again. Let's go to facts about correlation. It was a good picture here. Okay, so here we have 6 scatter plots. And their correlation coefficient is provided with them. So first, if we look at the 2 on the bottom left, do we agree that their coefficient should be positive? If you had to associate that with a line, do you agree that that line would be moving upwards as you go left to right? And if you look at the 2 on the bottom right, would you agree that their coefficients should be negative? That if anything, we have a line that goes down left to right. Okay, now look at their strengths. Which of those 6 graphs is the most linear? The most that would fall exactly on a line. So we agree it's the bottom right, or at least graphically it looks like it's the bottom right. Yeah, very, very close to a line. Look at that correlation coefficient. First of all, it's negative. That just means it's going downwards. But look at its R value, negative 0.99. If you square that, what do you get? What's 0.99 squared? Whether you're negative or not makes no difference. What you get when you square it, you get 0.9801. That is extremely close to 1. That's an extremely strong correlation. Now, if you had to grade the various correlations as you've moved through these 6 graphs, what is the next strongest just graphically? The next one that looks most like a line?
The bottom left.
The bottom left, which is positive because it's moving upwards, but it's certainly not as strong as the bottom right. And look at its correlation coefficient. What's its R squared value? .81. 9 squared is 81, so 0.81, right? Which is fairly strong. It's over 0.8, but not nearly as strong as a negative 0.99. Of the remaining 4, which would you say is the next most linear? The middle right. Will we agree on that one? But it's already getting to the point where it's really not tight at all. It's kind of very loose. And in fact, what's its correlation coefficient? Squared, I'm sorry. What's its R squared value? 0.7 squared should be 0.49, which is less than 0.5. We're already more than halfway to 0, which is pretty moderate. And after that, which one would you say is the next most linear of the remaining 3? Of course, we're getting to the point now where we really even start to question whether it is. Try that again. I couldn't get the words out. We're questioning whether it is even linear at this point. I mean, they're so unlinear that its R squared value are kind of small. What's the R squared value for 0.5, for an R value of 0.5? 0.25. This is very close to 0. And then if you look at the top row, I mean, the top row, they just look like blobs to me, just like a blob of points, especially the top left. Do you even see a line in the top left? Is there any one direction that stands out as as this is the line that I don't even see a line, right? It's as blobby as you can get, which is why its correlation is 0, right? There's no line there whatsoever. The one on the right, they're claiming R equals negative 0.3. Do you see a negative line there if you had to pick one? I mean, push comes to shove. If someone said you got to make a choice, positive or negative, I'd be like, okay, yeah, it's kind of negative. But look at its R value. It's so close to 0 that its R squared value is going to be even closer. Its R squared value is less than 0.1, a very, very low R squared value. So R squared values near 1, very linear. R squared values near 0, very nonlinear, very weak, or not even existent. R squared values somewhere in the middle, moderate. And in the next chapter, we'll give like definitive ranges from this number to this number, weak. From this number to this number, moderate. From this number to this number, strong, and so on. For now, it's just ballpark figures. Does that make sense? Questions on that? No, it doesn't make sense, or no, there's no questions? Or no, that was like a few minutes ago.
No question.
No questions. Okay, so facts about correlation. Okay, so there are some facts that you should know. So first, to reiterate, both variables must be quantitative. Okay, you can't plot categorical data. It doesn't make any sense. You need an X value and a Y value. You got to be able to put them into a formula. They must be quantitative. If you want to add categorical, we do that with shapes and colors, but you must have quantitative data. Okay. 2, only measures linear strength. You can have the strongest nonlinear association, and this formula will not provide it for you. It only provides linear strength. And just be aware, just because you have a high correlation coefficient does not always mean it's linear. You could get like 0.9 and still not have linear data. So just in case, always graph. Just in case, always graph. Because you don't want to assume that it's linear because your correlation coefficient is high, only to look at the data later and say, wait a second, this is curved. This isn't linear at all. So always graph the data. 3, correlation is non-resistant. Can someone remind me what non-resistant means again? What is non-resistant? New message here. It says it changes. Well, I think I know what you're trying to say, but I'm not the happiest with how you're saying it. What do you mean it changes? What does it mean? It changes. So, and not it's affected by outliers. Yes. Okay. Non-resistant means it's easy to change. Not that it changes, but that it's easy to change. It's really affected by outliers. Okay, that's a really great way of doing it. It's affected by outliers. Okay. And the last one is kind of new. Correlation is not a complete summary of 2 variable data. And this is a little more of an advanced concept. There's something in math called a sufficient variable in statistics. A sufficient variable means giving me this is all I need. Any extra information you provide, redundant, don't need it. This is sufficient for me to determine everything I want to determine about the data. An example of a sufficient variable is the average, the mean. If I want to know the average of something and I take a sample size of 100 and I say, here's my average. If you actually tell me all the individual data points, it won't affect anything. I already have my average. I don't need anything else. The average is sufficient for me to get whatever it is that I need. What it's saying here is that correlation is not sufficient. It's not a complete summary of two variable data. If you provide more information than just the correlation, that can actually enhance my understanding. Okay? Does that make sense conceptually, at least? I hope so. Okay. Other than that, this is chapter 4. Very, very qualitative, not very mathematical, and the little bit of math that we did was mostly in our calculators anyways. In fact, what we did is some of next chapter. So on Thursday, when we get to chapter 5, it's not all going to be reviewed. We didn't cover all of chapter 5, but some of it will be like we saw last time. We can do this. And then we're going to go and spend the rest of it. We're not going to go to 6 tomorrow on Thursday, but we're going to go back and we're going to look at the workbook and do some problems from there for correlation and regression, which is chapter 5. Okay, so unless there's any other questions, we are done for today.
Is your office hours are today at 5:40?
Yeah. Yeah, I mean, I'll be there. I close the room so I can transfer my recording to my computer, and then I jump back into the Zoom 2 minutes later. So I'll be in there very quickly.
Okay.
Okay, Lila, that's great news. Crystal, can you show the 4.5 example again, please? The 4.5, this one here? Okay, no problem. For the rest of you, I hope you learned something today. I hope you had as much fun as I did. And I hope you go on to live lives of religious fulfillment. And I will see you all on Thursday.
Professor?
Yes,
What day is your office hours?
today.
Today. Oh, okay. Is it Tuesday and Thursday, or is it?
Well, it's also Thursday, but mostly today. I have a little bit on Thursday, but today is the big day. You're welcome,
All
everyone.
right. All right. Thank you.
Okay, no problem.
Thank you. Have a good evening.
You should.
Hello, Professor.
It's okay. I don't know what that is. I'm gonna write that down because I've never heard of that. Tajin, Tajin with lemon. Hold on. Food comes first.
Professor?
Food comes first. Hold on. Tajin with lemon. Okay, I'm gonna write that down. Okay. Yes. What's your question?
I think I heard you call my name that like before you entered the meeting.
Who are you?
Layback.
I was probably taking attendance. Does that count?
Oh, I'm not sure. Like I just heard it, but I'm like, oh wait, bye. Or unless you're calling for another student with a similar name, I'm not sure.
It could have been. I don't remember. I don't.
Okay, maybe I misheard.
It could be.
Just making sure.
Yeah, no problem.
Have a good one.
You too. Take care. As soon as there's no more questions, I'm gonna go and close the meet so I can transfer the recording to my computer and then rejoin the meet right afterwards. So like literally 30 seconds after I close it, I'll be back in. So if you have a specific question, then just rejoin after 30 seconds and I'll be here waiting for office hours. Okay, everyone?
Professor, I have a quick question, sorry.
Go ahead.